overlapping information with what you had in your engineering geology. There are differences between the engineering geology and, let's call them the geo-techniques, which is basically under the discipline of civil engineering. So engineering geology, geophysics, shallow geophysics, and things of that sort fall under the College of Science. For us here, we are looking at application of solid mechanics into soils. So what that basically means is that all the material that you covered in your mechanics of materials, structural analysis, overlapping with portions that we taught in our concrete class, now you're going to see application of that in the soils. And there's major difference between the two. In fact, if you're looking at different types of civil engineering materials that we have soils that are going to be behaving very differently, and is going to have entire different ramifications in terms of the mechanical properties. So give me a few examples of civil engineering materials that you're familiar with. Steel.
Concrete.
Concrete. Wood. Asphalt. All right, so let's go by the list that you mentioned. Steel. How do you characterize steel for your steel design? I'm assuming that the majority of you here are seniors, so you went through the steel design. What are the parameters you need in order to design a steel structure or steel as a material?
Tensional strength.
Let's go back to 1301, freshman level course. What kind of test would you use to characterize the modulus value of your steel? Steel in tension, right? So remember, you subject the steel into monotonic tension and you see the necking effect, and there will be a rupture at some point, right? Remember what the stress-strain curve looked like? When we don't have the board, I have to do it with my hand. This would be your stress, this would be your strain. It goes up, and then there's going to be a plastic component to that, and then you see the rupture, right? What was the modulus value? How do you calculate the modulus value there? The slope of the stress-strain curves gives you the modulus value, right? We call that the modulus of elasticity. Did we ever talk about the changes in the modulus of elasticity for the steel? No, right? You plot your stress-strain curve, you find the slope there, and you have one number. That would be your modulus value. Let's contrast that with soils now. Soils do not have one modulus value. Soils are stress-dependent entities. They are stress-dependent materials. What does that mean in terms of the civil engineering aspect of that? What that means is that, let me give you one simple example that probably would be more tangible to understand. Let's assume that I have a cylindrical sample filled with soil particles, right? I apply the load from the top. What happens? I compact the soil, right? I press the soil from the top. What happens to the volume of the soil? Volume decreases, right? What happens to the solid, weight of the solid particles in there? Stays the same, assuming that there is no moisture evaporation there. So you basically, the weight of the solids, the weight of the water stays the same. Well, what happens to the volume? The volume goes down. Can you tell me what happens to the density of the soil? The density of the soil will increase, right? So the density is simply weight or mass, excuse me, weight or mass divided by the volume, right? The mass or weight stays the same, the volume goes down, the density will be higher, right? So what happened? The soil densified underneath the pressure. What happened to the stiffness properties of that soil? Increased, right? And if I apply more pressure, I can kick out more air void in there, and you get better interaction between those solid grains, and ultimately you'll have a better medium, right? So the stiffness properties are a heck of a lot higher compared to what it used to be before in terms of the loose soil. So the ramification of that is soil do not have one modulus value. They do not have one stiffness properties. By the way, stiffness and modulus are different entities and different concepts. You have to be cognizant of that. Unfortunately, a lot of times they've been mistaken in the industry, and also that has some issues when we get into the design aspect of it. All right, so soils are stress sensitive, as opposed to what we talked about in terms of the steel. How about concrete? Do we have different values of modulus for the concrete? Yeah. Modulus value of concrete changes quite small amount, depending on some parameters such as creep, such as other issues related to the shrinking and also hydration of the cement inside the concrete. But let's put that aside. For design purposes, you always assume that the modulus of concrete is one value, right? The modulus is not changing. Can you give me a good number for the modulus of a concrete slab?
4,000 PSI.
4,000 PSI. Are you talking about the F prime C? I'm talking about the modulus value. See, this is the difference between the strength and modulus. Unconfined compressive strength, and then we're talking about modulus. A good number for modulus of a concrete slab.
600.
Between 5 million psi to 7 million psi, that would be the modulus of the concrete slab. Right? That would be a modulus of a reinforced concrete slab, ranges around those numbers. But if you're looking at, say, for example, a small micro cracks that happens during the service life of that concrete slab, let's assume it's a rigid pavement, for instance, that will result in reduction of the modulus value. Right? So there's some damage, and that damage essentially translates into lower stiffness properties. That's for the concrete. Now how about, you mentioned about the wood in terms of other engineering material that we have. First of all, tell me how you determine the modulus value or stiffness properties of wood in the lab. Add that in your materials class. I'm assuming that you went through the 3-point bending test and also the compressive test. You basically test the material at perpendicular to the fibers and vertical to the fibers and parallel to the fibers there. And then you get an indication of the stiffness properties of the wood. But in terms of the soil, we're basically looking at an entirely different components there. So the first thing that we have to keep in mind is soils are stress sensitive. The ramification of that is the modulus value changes, the stiffness properties change. Also, we have to be careful that you cannot assign one modulus value. And soils are non-homogeneous materials, right? Can you tell me what are the typical constituents of a soil that I can sample from outside right across the street here? I'll go right across the street, grab a barrel and a bucket and a shovel and a pick and put in soil in it, bring it to the class. What are the constituents that I have in that bucket? You have solid grains. You have air that is trapped in between those solid grains. What else? Moisture, right? So let's assume that you don't have any contaminants. Let's say I go to the airport and I sample some soil. Because of the fact that there's some fuel spillage there, you see that there's another component in there as well. So let's assume that we are not looking at those components. So soils are non-homogeneous. They're consisted of different types of material or different phases, in fact. Consider the solid grains. Could be that sandy material, gravelly material, clay material, silt material. We'll get to that. So that would be entirely different discussion. But you have solid grains, you have air voids, and you have moisture that is in there. Multiple phases. In fact, our next lecture is going to be about phase diagrams, to see how we can separate these phases of material and use diagrams to be able to figure out what are the volumetric relationships and weight relationships of the materials. So, stress sensitive, non-homogeneous. Are soils linear or non-linear materials? Non-linear. It's actually highly non-linear materials. In fact, if you look at the stress-strain curves, for the concrete, because of the fact that concrete is a brittle material, you see that the path of loading is going to be linear. At some point, if you increase the magnitude of the stresses, you see that the concrete cylinder will shatter, right? You don't see the plasticity in the stress-strain curve. On the other hand, if you're looking at soils are extremely plastic material. So again, the ramification of that is when you're looking at decomposition of the strains, tell me what the strain is. Mechanics of material. What's the definition of a strain? Right, you're basically looking at original length or original shape divided by, you have the original shape and you have the change in the shape, right? So if you're looking at the volumetric strain, that would be the change in the volumetric behavior of the material, or if you're looking at the vertical strain, that would be the change in the vertical direction divided by the original height of the specimen, for instance, right? So you have basically, you know what the strains are. And you can essentially subdivide or subcategorize the strain in the material, meaning that a portion of the strain is going to be elastic. Now tell me from your mechanics of materials, what's the definition of elastic? What happened? No, all right, we talk. So we have the strains. Do you know how you can decompose the strains? We talked about the elasticity part of it. What's the definition of an elastic material? Exactly. As Valeria mentioned, we're looking at a deformable body. You apply the load. What happens right underneath the point load here? You see the deformation develop right underneath that. As soon as I remove my hand, the deformation will bounce back, right? So there is going to be a fully elastic material. The fully elastic material essentially means that all the strains are recoverable. What's the implication of that? There is no permanent component to the strain, right? So there is no plastic strain. Plastic strain is synonymous with permanent strain or permanent deformation. Can you give me an example of permanent deformation? Good point, Jeremiah. Let's think about it, for instance, in terms of the pavements. Right? All of you probably drove or sat in the car or just somehow got on I-10 and got here, right? So if you look at the wheel path, sometimes you see some deformations in it, right? So we call that rutting. Rutting in the wheel path is essentially the permanent deformation associated with the repeated loading of vehicles. Right? So rutting is permanent deformation for us. Now let's think about it in terms of this structure. So this structure is built upon the soil, right? All geotechnical structures are essentially, not geotechnical, all civil engineering structures, in one way or another, deal with soils, right? We build the structures on soil, so we have to figure out what are the contribution of that soil platform is in there. So let's think about it now. Let's assume that we are looking at physical science building. Let's assume that we are not looking at the connection between the classroom and the skywalk. Let's assume that this is an isolated building by itself. So the building is built on the foundation, right? So there's a foundation, and then there is going to be the natural soil, right? The typical soil that we have. So typically, the structure that we have here is consisted of concrete material, the steel material. Those are good quality material that can basically sustain its load. And then the role of the foundation there is to transfer the loads to the weakest link that we have. What is the weakest link? The soil, right? The soil, you know that it cannot sustain high amount of load. Oftentimes, you step your foot in there and you see your shoe impression will be on the soil. So that basically, that's the permanent deformation, right? So we have to be able to design the foundation in a way that can transfer the loads through the platform, through the soil, and bring the stresses down to a level that the soil can tolerate. We know that the soil cannot tolerate much. So you have to basically distribute those loads, and that basically translates into the concept that you had in your structural design, mechanics of material, concrete design, that we called it the dissipation of the energy, or dissipation of the loads there, right? So what happens, for instance, if you have multiple layers, or that platform that you have, it basically transfers the load into the platform and distributes it in the soil, right? It basically brings it down to the level that the soil can tolerate. That's basically what it means in terms of the loads. All right, so soils are highly nonlinear material. The plastic strain component is significant, and therefore you have to be able to account for that. Now, the next component of the soil is that, remember we're talking about non-homogeneous material, stress-sensitive material, meaning that the modulus value changes with the amount of stress that you apply on it. And they're nonlinear material as well. Now the fourth one on the list is soils are anisotropic materials. What's the definition of anisotropy. What is isotropy? Yes, exactly. If you dissect the word, this is weak. Anisotropos. So basically it means that non-similar properties. So the material properties are essentially different in different directions. That's basically what anisotropy means. If you want to write it down, anisotropy is directional dependency of material properties. In very simple terms, it means that the modulus value in the vertical direction is different than the modulus value in the horizontal direction. So previously we talked about, for instance, concrete, wood, and also the steel. We never considered the anisotropic effect of those materials. But for soils, these are highly anisotropic materials. All right. So another thing that we have to keep in mind is where the anisotropy is coming from. Right? Soils these are particulate materials, right? They're particles that are at the top of one another. Right? So do they have similar shape or do they have random shape? Completely random shape, right? They are not spherical, they are not equidimensional, like a cube, right? They look different from one another. What happens if I compact the soil from top? So let's, for example, that we go out on I-10 and we see that the drum rollers are passing over the soil. What does a drum roller do? Compact the soils, right? So apply the compaction energy from the top. There are different ways to exert that compaction energy. It could be based on the static pressure of that drum. It could be based on the vibration of that drum, kneading action, manipulation, and also the impact. Those are the different mechanisms that compactors use in order to densify the soil. So you have the load that is happening from the top. Let's assume that I have a flat and elongated particle that stays like this, that is like that. What happens if you apply the compaction energy from the top? Yes, basically Margarita was showing that with hands. For those of you who missed it, she was showing that it aligns itself with the horizontal plane. Right? So it basically falls flat on the side. So what happens if I apply the load from the top, you basically have enough area to resist that load. But what happens if you have shear forces from the side? Basically it deforms very easily. So let me get back to that again. Soils or particulate systems are frictional material. Soils are frictional materials. Very different from the concrete that you have. Because in the concrete you have the mortar, you have the aggregate, and basically you have adhesive bonding between the material. Soils, do we have any glue in between? We don't. We just have moisture and solid grains there, right? So everything is based on friction or interlocking effect between the solid grains. So if they lock very well together, you basically have a very robust platform or a very robust medium. Otherwise, if you have, say for example, let me give you some example of that. We're going to talk about this a little bit in more detail later on. Let's think about the geometry of the particles. I just mentioned that you can have spherical particles, or you can have completely flat and elongated particles. Those are two ends of the spectrum, right? But in reality, we know that our solid grains or soil particles are essentially random in shape. They're not going to be fully spherical or cubical, and they're not going to be completely flat. Something in between, right? And for that reason, when you apply the compaction energy from the top, you have preferred orientation of the particles, right? If you have flat particles, far end of the spectrum, you basically will see that they lie flat at the top of one another. We talked about soils are frictional materials. From your static course, how do you calculate friction? Right, so you have basically the normal force, and you need to know the coefficient of friction. In very simple term, again, let me give you a tangible example. You have two ends of this spectrum. Let's assume that I have two very smooth surfaces. Let's assume that I have two mirrors with moisture in between. Right? Does it require a lot of force to mobilize these two past one another? They easily pass one another, right? So there is not much of interaction between these two particles. Right? On the other side, let's assume I have those two pieces of mirror, but I coated them with sandpaper. You have two sandpapers. Okay, thank you. At least one improvement, right? All right. So we have two sandpapers. It requires a lot of force to be able to mobilize them past one another, right? So that has to do with the interaction of those particles there. So if you have smooth particles, or if you have particles with high texture gravity. Texture is essentially that surface asperities or the macro texture of the particles. We have some, for instance, if you're sourcing your aggregates from the riverbed, right? The riverbed, those are very smooth aggregates. So do you think that would be a good idea to use those for the foundation of an airfield runway? No, right? So you as design engineers, you will see that, for instance, TxDOT, for instance, requires you to specifically use particles that are crushed. And they test them, and you're going to test them too, in fact, in one of the labs, with a device called Aggregate Imaging System, or AIMS. And this AIMS, essentially, you can look at three components of these aggregate particles. You're going to look at flatten elongation. We call them the form factor. You'll look at the angularity of the particles, which has to do with the broken edges. And ultimately, you can get an indication of the surface asperities or the macro texture or the surface texture that we talked about. So all of these components are going to tie itself into interaction between the particles. So if you want to have only one takeaway from this lecture is that soils are frictional materials. Soils are frictional materials as opposed to other materials that you're familiar with. Other material that you're familiar with, such as concrete or asphalt, for instance, there is a glue in between, right? You have asphalt as the glue. Essentially coats the fine particles. We call them the mastic. You have the mastic and you have the aggregates. You basically have a good bonding between the aggregate and the mastic, and therefore you have a very robust platform. On the other hand, for the concrete, you have the mortar, right? You have cement, you have aggregates, you have water. Just mix them together and create your concrete there. So those are different. But for soils, now you have to figure out what would be the amount of moisture that results in the best packing after the compaction. So for us, we call that the optimal moisture content, and that's going to be one important lecture that we're going to talk about in terms of the compaction of the soils in the lab and compaction of the soil based on the compaction energy that we have. All right, so in terms of the mechanical properties, let me just quickly outline that here for you. I hope I can write it big enough so Rafa from the back can also see that. So, mechanical properties of soil. All right, remind me what are the parameters that we talked about? Yes, they're non-homogeneous, they're non-linear.
Stress dependent.
They are stress dependent.
Isotropic.
Yes, they are frictional material. They are anisotropic. All right, so let's first talk about that nonlinearity that we talked about. So I'm looking at this stress strain curve. This is a path of loading, and this is a path of unloading. So I load the system, goes all the way up. I remove the load, it goes all the way back to the origin. What kind of material am I dealing with here? I heard both of them.
Elastic.
Is it elastic? Is it plastic? Or is it somewhere in between?
Elastic.
Elastic. What was the definition of elasticity? All the deformation will bounce back, right? Therefore, there is no strain deposited in the material, right? So this would be for a linear and elastic material. Do you agree that this is a linear curve? Linear curve, oxymoron. It's a linear, and also it's a elastic material because the deformation went all the way back to the origin. All right. Is soil like this? Does soil behave like this? No. This is the path of loading, and this is the path of unloading. What kind of material am I dealing with here? You have to tell me two components. Is it linear or is it nonlinear? Nonlinear. So all the deformation went all the way back to the origin. So what kind of strains am I dealing with? Completely elastic material, right? There is no component of plasticity in there. Therefore, tell me what should I write here? It's nonlinear and elastic material, right? Can you give me a good example for this type of material, a civil engineer?
Rubber. Steel.
Should be very small strain behavior of a very strong material. So that basically could be that. This is idealized case. We don't have this. This one, we might have that. All right, so let's move that off since we're talking about materials. Can you tell me what kind of material is this? I loaded the material. There's a small degree of nonlinearity in the material, but at some point it shattered. I cannot just have the second component of the stress-strain curve, as you can see here. Do you agree that this is a brittle material? It could be concrete, it could be a piece of glass. There's a small amount of nonlinearity there, but it shattered after a certain amount of stress. All right, tell me what this one is. Let me help you. Let's take a look at that. I loaded it, came all the way to here, and then removed the load, came back down. Portion of the strain bounced back, but the other portion is deposited in the material. What kind of material is this? Non-linear elastoplastic. Because there is a elastic component to it and there is a plastic component, right? So it's a non-linear elastoplastic material. Soils behave more like this. These are soils. Can you tell me what kind of material am I dealing with? applied the load, went all the way to here, removed the load, came down back here, and then it took some time for a portion of it to recover, and then a portion of it stayed in the material. So there's a time-dependent component that is associated with this kind of material, with the recovery of the strains. That's non-linear. Elasto. Yes, this is the component of viscoelasticity. So it's a viscoelastic material, such as all the polymeric material that you're familiar with, such as asphalt. Right? So asphalts behave like this. This is asphalt, this is soil, this is concrete. So now you know what all these different types of material that we are dealing with, and that puts in perspective of what soils are and what other materials that you're familiar with. All right. Anisotropy had to do with the directional dependency of material properties. When we talk about the soils, we get into this discussion here. Now, the last one on the list is that soils have memory. So, hopefully in chapter 9, you're going to see that we can run some tests to see what would be the maximum pressure that this soil has ever experienced during its formation in the past several million years. You can have a test. It can tell you exactly what would be the maximum stresses that were placed at the top of the soil based on the layering of the soils and all the formations and anything related to that. Very interesting. They have memory there. They might be at the side of the road right now, but several million years ago it was beneath layers. But we have some tests to be able to get that. Concrete doesn't have this component. Asphalt doesn't have that. Wood doesn't have this. But soils do have memory, and we have tests, and you're going to see those tests, and hopefully run them in the lab to be able to find the pre-compression pressure or the maximum past pressure of the soil. So these are typically what we have to talk about in terms of the general mechanical properties of the soil. We're going to tackle each of those and each components later on together, but let me go back and quickly tell you a little bit about the things that we have to do in this course with regard to covering the material and also our lab testing, the grading policies, and everything else. So you know that based on what we have and based on the syllabus that you have, you're going to have 3 exams, you're going to have 7 lab reports, and you're going to have 6 sets of homework assignments. Again, make sure to submit them in a timely manner. You have 2 TAs, the information about the TAs, their email, and also their office is listed on the syllabus. Please take a look at that. Everything associated with the lab reports and homework assignments goes directly to the TAs. Please don't CC me on those. Don't send your homework to me. They have to go to the TA. Right? So everything related to that, to the homework assignment and also the problems in your homework assignment goes there. If you have questions about the concepts, now you come to me. And you're welcome to come by the office whenever you want. It's better to send a short email, so I'll be in the office so we can talk about that. All right, in terms of the lab, how many of you took materials for engineering last semester? All right. So please go and check with either the office and also all the environmental safety department that we have here at UTEP. So typically your lab safety workshop is valid for 1 year, right? So you saw my email, I asked you to go and attend one of those. So if you already attended that last semester, it should be valid, but it is your responsibility to check it. So check and make sure that your lab training or lab safety training is still valid for this semester. If it is valid, you don't need to go. And you have to go to the one. Where's Mr. Tarin? Yes. So the one that you have to go to is basically the one that says the lab safety training. If you did it in the previous semester, you can look at the refresher one. Right. So don't go to the other sub that you have.
Okay. Because there's 2 options. There's like a refresher one, and then there's
Right, refresher, you don't need to do the refresher. Yeah. If you did the one that is in the previous semester, you can do the refresher, but since it's going to be valid for 1 year, you really don't need to do that. So take a look at the lab safety training. And you have to have it by university rules. Your TA will check that with the environmental safety department the first day that you have to go to the lab. And if you don't, you're not going to be allowed in the lab. That's the university rule. Even the president of the university cannot override that. It's a UT Regents basically. All right, so that's one thing about the lab. The second thing about the lab, I specifically asked your TA not to allow any switching between the labs because of the fact that we have limitations in terms of the space and limitations in terms of the equipment. Talking about the equipment, you are the luckiest group that are taking the Geo-tech. Because in the past semester, back in September, I purchased about a little bit over $60,000 of new equipment, and just last week we put in another $15,000. So you guys are the group that are going to use the new equipment. So all the equipments that you will have are going to be new and top of the line. So lucky you, I cannot say the same thing 5 years down the road. All right. So our lab is in very good condition, but one thing that you have to note is that because of the fact there are more than 100 of you in this class, and also we have 4 lab sections, notice that labs are going to be crowded. You have to clean the labs right afterwards. So be very diligent about that. This is something that we have to make sure that our labs are taken care of for that. In fact, we're going to have ABIT visit. Are you familiar with what ABIT is? It's basically the university accreditations. They're going to come in and they're going to take a look at our labs. And if it's a mess, they're going to evaluate the accreditation of the program. You don't want to graduate from a program that is not accredited. Can't find a job, basically. So that's another incentive for you to make sure that we're taking care of our labs. All right. In terms of the attendance, you probably noticed that there are some devices at the door. So what I would ask you to do is tap your card when you come into the classroom. That's all basically you have to do. And you can tap your card about 30 minutes before the class and up until